Thank you very much, Javier, for the introduction, and good afternoon and good morning or good evening, depending on where you are. I will be discussing today our work on the impact of PLL dynamics on the small signal stability of the modular multi-level converter using a dynamic phasor model in the stationary ABC frame. So the MMC has become the prominent choice in the VSC HVDC systems in the past decade. This has mainly to do with the superior harmonic performance, decreased switching frequency, and lower losses associated with the MMC. However, at the same time, the small signal modeling of the converter presents theoretical challenges. The MMC has a unique internal dynamic behavior, which is characterized by harmonics at multiple frequencies, and in the presence of such harmonics, it becomes challenging to obtain a time-invariant operating point to perform linearization. These harmonics are generally neglected in small signal stability studies. However, in our previous work, we showed that these harmonics actually do result in changes in the converter eigenvalues. We were able to show this by using the theory of dynamic phasors, which makes it possible to capture time-varying dynamics in an LTI manner. In addition to the harmonics, the phase-locked loop is also a crucial element in the small signal stability. It provides the transformation angle for the commonly utilized DQ controllers, and it is already known to cause stability issues in, for example, weak AC grids. So, for instance, when the AC grid is weak, then an imperfect PLL would mean that the wrong synchronization angle would be calculated, and then there might be problems with synchronization of the controllers with the system, leading to potential instabilities. The impact of the PLL on the small signal stability of VSC HVDC systems has previously been studied in the literature. However, the main focus was on two-level converters. Recently, there were some works focusing on MMC HVDC systems as well. However, these were mainly using simplified models, which do not contain the theoretical challenges that we encountered in our model. Moreover, the interaction of the PLL with voltage harmonics that are present in the PCC, as also presented in one of the previous presentations by Yonggang. So the previous models do not cover this the interaction of the PLL with voltage harmonics in the PCC. In this paper, we present an analytical small signal state space model based on the theory of dynamic phasors, and this MMC model includes the PLL dynamics. We make use of the component connection method to avoid algebraic loops, such as the one that can be seen over in this figure, in the figure in this slide. More details can also be found in the paper. And the model has state variables in the stationary ABC frame, and it also includes the interaction of the PLL with PCC voltage harmonics. So following this introduction, I will be guiding you through the development steps of the model, and then I will show you how we validated our model by conducting time domain step tests, after which I will be presenting results of a small signal stability analysis study. But before, I would like to briefly mention the theory of dynamic phasors and some properties associated with it. So the theory of dynamic phasors relies on the assumption that a generic signal, x of t, can be written as a linear superposition of its time-varying Fourier coefficients, capital Xk of t over here. These capital Xk of t, the time-varying Fourier coefficients, are called the dynamic phasors, and they can be obtained by this moving averaging operator over here. And in this paper, we make use of a special notation to refer to the dynamic phasors. While developing a dynamic phasor model, we need to keep in mind some mathematical properties, such as the relation of the time derivative of a dynamic phasor, which includes the j omega terms, and also the multiplication of two signals being represented as a convolution of the dynamic phasors. And finally, these dynamic phasors are complex valued, but as an end result, we would like to obtain a real valued model. So we need to represent the real and imaginary parts of the dynamic phasors as distinct state variables. When we are developing a dynamic phasor model, for each and every steady state harmonic that we have in the trajectory, we include a dynamic phasor model, which is then represented using two state variables, one for its real part and another for its imaginary part. And then in this sense, the dynamic phasors become the state variables rather than the voltages and currents. Now, a bit on the MMC model that we consider in this paper. So we developed a model of an arm average model of a three-phase half-bridge MMC, so the switching effects were excluded, and the capacitor voltages are modeled using a control voltage source, as can be seen over here. The model has state variables in the stationary ABC frame. The DC side is represented using a constant voltage source. At the AC side, the AC grid is represented using an ideal voltage source in series with an impedance ZG. The converter transformer is represented using a series impedance ZT, and in between them we have the point of common coupling. In this paper, the maximum frequency that is included in a dynamic phasor model is defined to be the bandwidth of that specific model. And also, as also presented by Caroline in the previous presentation, we make use of the commonly utilized sigma delta formulation to change the state variables from the arm coordinates to other coordinates. And yeah, here I'm presenting the state variables associated with the dynamic phasor model, which has a bandwidth of 300 Hertz. I think I will not go too much into detail of this, and more details can be found inside the paper. But basically, we include different state variables for the different harmonics that we have in the steady state harmonic trajectory. Now moving on to the control architecture. The controllers make use of uncompensated modulation, and both inner and outer controllers are considered. For the inner controllers, we make use of standard DQ frame-based controllers, and the outer controllers include the active and reactive power control, the PLL, and the energy controller. For the PLL, we make use of a standard one with a low-pass filter at its input. So here, VPLL represents the output of this low-pass filter. Epsilon PLL is the error state of the PI controller of the PLL, and theta PLL is the angle that is tracked by the PLL. Now I would like to briefly explain how we apply the component connection method. So here you can see the different controllers that we included in the model. So when we are developing the model, the differential and algebraic equations associated with these controllers are separately developed and linearized to obtain the subsystems that can be seen over here. In the same fashion, the MMC model is also separately developed and linearized. At this point, these subsystems are not connected, but then we connect them later on using the interconnection matrices L1 to L4, which satisfies this linear relationship that can be seen over here. So these interconnection matrices connect the subsystems with each other, and also with the overall input vector A and the overall output vector of the system B. Now I would like to explain the theoretical challenges that we encountered during the development of the model. The first one is associated with the Parkes transformation between the stationary ABC frame and the rotating DQ frame. So as you can see over here, the transformation matrices between the ABC and the DQ frames are time periodic. So they contain terms that are oscillating with a frequency of n omega. In the dynamic phasor context, we need to represent these matrices as their dynamic phasor equivalents, and we do this by applying applying the moving averaging operator to each and every component of the matrices. When we do that, we see that as long as the frequency of these matrices are equal to the nominal system frequency, there's no problem. We can calculate a dynamic phasor equivalent. However, during disturbances in the system frequency, the components become null, and we cannot really calculate any dynamic phasor representation of these matrices. The solution that we come up with is to design the PLL to track omega PLL, which represents the deviation from the nominal system frequency omega g. And in fact, this is actually equivalent to having two different DQ frames, one global DQ frame rotating with omega g, and the other, the converter DQ frame rotating with omega g plus omega PLL. In this context, the transformation between the stationary ABC frame and the global DQ frame is given by this convolution operator. And the rotations between the DQ frames, the converter, and the global DQ frames can be obtained using these trigonometric rotation matrices. And of course, more details can still be found inside the paper. The second theoretical challenge is associated with the harmonics that are present at the point of common coupling. So in this paper, the model with 300 Hz bandwidth contains some harmonics at the point of common coupling, for instance, the fifth harmonic. And this is the case even when the AC grid contains no harmonics. So we calculate the PCC voltage using this linear relation over here. And we can see that even when there are no harmonics at the AC grid, sorry, because of the harmonics at the output current and the converter output voltage, the PLL input, the PCC voltage will contain harmonics. And this fifth harmonic is actually translated to a sixth harmonic because of the DQ transformation. And this results in six harmonic components in the PLL state variables. Then we encounter the problem that is related to the definition of this sixth harmonic PLL, the sixth harmonic dynamic phasor of the PLL angle, because when we would like to calculate this moving averaging operator for the rotation matrices, we see that the integrator becomes a nested cosine function, which is harder to solve. To solve this, we made use of trigonometric approximations, as the sixth harmonic component in the PLL angle is rather small. So when we apply these approximations, we are able to represent the rotation matrix in this linearizable format. And by doing that, we are actually able to model the interaction of the PLL, so the interaction of the harmonics in the PLL with the other harmonics inside the states. For instance, I won't go too much into detail, but we see that even for the DC components in the DQ frames, we see some effect of the sixth harmonic component because of the convolution of the dynamic phasors. Now moving on to the validation of the dynamic phasor model or the dynamic phasor models. In this paper, we considered two different dynamic phasor models, one with a bandwidth of 150 Hz and another with a bandwidth of 300 Hz. The number of state variables can be seen in this table over here. And these models are validated in MATLAB Simulink by conducting small signal step tests in time domain. For the step tests, we consider a relatively strong AC grid with a short circuit ratio of 10. And yeah, more details on the operating point and the controller gains are also given in the table, in the paper, sorry. And we are actually here depicting the responses of the circulating current in phase A, and we are able to see that the response of the nonlinear average model, which is denoted in blue, is accurately captured by the dynamic phasor model with a bandwidth of 300 Hz, whereas the dynamic phasor model with a 150 Hz bandwidth is not able to capture this time-varying behavior. And the model with 150 Hz bandwidth is actually corresponds to the neglection of the harmonics, of most of the harmonics. Now moving on to the small signal stability analysis, we made use of the state space formulation of the dynamic phasor models, and then we calculated the eigenvalues of the A matrix, as it is commonly done in power systems. We did this for a relatively weak AC grid with a short circuit ratio of 2, and this showed that when the PLL is included, so the eigenvalues that are plotted in as red dots, we see that there are modes with a low damping in the dynamic phasor model with 300 Hz bandwidth. So here this black line indicates 5% damping, and we see that as the modes that are indicated with the green circles, there are some modes that have damping less than 5%, specific to the 300 Hz model when the PLL is included. When we carry out a participation factor analysis, we saw that these modes, these low damping modes, are actually associated with the PLL states, such as the angle or the PLL controller error, and the internal converter voltage and current harmonics, such as the fifth harmonic capacitor voltage difference, the fifth harmonic output current, or the fourth harmonic circulating current. We took the analysis further and analyzed the effect of the cutoff frequency of the PLL input filter, FPLL. The nominal value of this filter is 50 Hz, and in the analysis we vary this cutoff frequency from 25 Hz to 150 Hz. When we do so, we saw that there were major changes on the modes that are directly related to the PLL states. However, when we look at the zoomed photo over here, we see that there are also some modes that show changes, and these modes have frequencies between 200 and 300 Hz. Now moving on to the conclusions of this paper. In this work, we presented the development of a dynamic phasor model of the modular multi-level converter in the stationary ABC frame, and the model includes the PLL dynamics. The model was developed relying on the component connection method in order to avoid algebraic loops in the development. we saw that the MMC creates harmonics at the voltage of the point of common coupling, even when the AC grid is free from harmonics. And we showed that at the model that we developed or presented actually incorporates the interaction of the PLL with these harmonics. And finally, we presented that the PLL harmonics actually result in modes that are affected by both the inner converter harmonics and the PLL itself. And the PLL filter cutoff frequency, FPLL, is shown to change the damping of such modes. I would like to thank you for your attention, and now is the time for me to answer your questions. Thank you.
Thank you, Ozgur, for your nice presentation. So again, I don't see any question from the audience.
Okay.
Well, I I already knew your work because you have a publication about that in a journal paper about the phasor modeling with MMC, which is very interesting. In fact, you have a very it's quite complex model because you have so many state variables. So at the end, you have, as you can see, we have so many poles to analyze. It's very precise, but it's very complex in the same time.
Indeed.
To try to compare your method with other methods from MMC modeling and to see, because there are some, well, MMC is not simple. Right now, it's clear that MMC is not simple, but there are other methods. For example, one which has been developed by Gilbert Bernier in SynTef.
Yeah.
As you try to compare, well, I would say it's a general question, not exactly on your on the topic of your publication, a more general question about phasor, dynamic phasor, because I will try to compare a little bit, because here, in fact, you are doing, you are explaining, you are honest. You say there are some assumptions also. So, is it better than? Is it really better than other kind of method? Is your advice about that?
Thank you very much for the question. Of course, yeah. Now that I'm advertising my work, I will just, or our work, I will say that it's better from the others. But yeah, this improvement in the model accuracy also comes with a drawback. That is the number of state variables. So we are able to, like, yeah, not from the modes, but for over here, the model can actually integrate the effect of steady state harmonics and also the dynamic behavior of these harmonics. So in the works that in other works that we did until now, we showed that when you increase the model bandwidth from 150 hertz to 300 hertz, you are actually seeing some changes in the already existing eigenvalues. Of course, when you are increasing the modeling order, you are adding additional states into the model, so you will be seeing additional modes. Now, yeah, actually from right now, we are also still investigating the effect of those additional modes, and we are trying to see if they will cause any issues, any problems with the small signal stability, and also when would such cases be occurring. So that's still an ongoing research effort, I would say. But I can say that the 150, the dynamic phasor model that we developed, that has a bandwidth of 150 hertz, that covers the same harmonics as the model that you mentioned by Gilbert Berna. And yeah, we are actually, yeah, I think soon we will be publishing on that as well, a more, let's say, in-depth comparison of our dynamic phasor based models, and also on in comparison with other DQ frame based models. So yeah, it's there is an improvement in the accuracy, but it comes at a cost.
Yeah. Question, if you can have a short answer to the question from Patrick.
Yes.
In case of unbalanced conditions.
I'll try to see the question. Yes.
Could you say something in case of unbalanced conditions? Very short question.
Yes. Yeah, thank you very much for the question. Well, I can say that there will be some changes, so that is also something that we are analyzing right now. But yeah, some let's say adjustments are needed to accurately represent unbalanced conditions as well, because the relations between the converter outputs, so the frequency couplings need to be integrated in a more detailed way when the system is unbalanced. So here now the model is in the stationary ABC frame, so it can consider unbalances, but we didn't really test that in detail. So yeah, I'm assuming that there will be some changes, but I think in that case, the PLL modeling might also need to change, because the PLL right now we integrated as we only included a standard PLL in our model.
Okay,
I
thank
hope that
you.
was an answer, but yeah, if this doesn't answer, so you can also ask additional questions and I'll try to type my answer.
Okay, thank you, Ozgur, for your answer.